we use, and again, we're only solving systems of two equations, is using a matrix equation, which involves finding an inverse matrix. So today you want to be able to write a matrix equation and then know how to find the solution to a matrix equation so that you can solve a system of equations. So this first part is kind of laying out for you how we do this, how we set it up, and then how you find your solution, because it will be, or the way it's set up is the same for every single one. It's just when you have two different equations, then the way you work through it will be different. But it gives us a system of equations at the top and says you can write a matrix equation to solve this system, and that's what this is setting up here. So for this exact system of equations, this is what the matrix equation would look like, and it explains above how to write it. So everything in both equations that would be on the left side of the equal signs, you can write the left side of the matrix equation as the product of the coefficient matrix and the variable matrix. So ultimately, where it says above, it says A times X is equal to B. That is the general form of a matrix equation. Matrix A is the coefficient matrix in that matrix equation. And we found coefficient matrices before. You had to do that with Cramer's rule. They had labeled it as C in Cramer's rule, but same idea for the coefficient matrix. So if you look at your system above, notice in that coefficient matrix, the first column are the coefficients of your x's, and then the second column are the coefficients of your y terms. So it's that same setup as we had done with Cramer's rule. So it's the coefficient matrix multiplied by, and then the variable matrix is always going to be a 2-by-1 matrix, so 2 rows and 1 column. And it's just your two variables. So it's typically going to be x, y. If you had two different variables like c and d, it would be c, d. But it's always going to be just one column, and then in this case it'll be 2 rows because we only have 2 variables. And then it's equal to, the right side of your matrix is called the constant matrix, and that's matrix B in the equation. And that is just the column of constants from your system of equations. So in the system we were given, the constants are 9 and 3, and that's what makes up that column there. And again, that's going to be a 2-by-1 matrix, just one column, and you'll only have 2 equations, so you would have 2 constants. So we are going to practice taking a system and then writing it as a matrix equation. So this is the setup for it. But ultimately, in order to solve a matrix equation, what you're going to see is the way you solve it. You're always solving it by multiplying 2 matrices together, and you just have to know which 2 matrices, and then make sure you have the order correct, but it's the same setup every single time. So in order to explain how these are solved, what this is doing, it's comparing how we solve equations with just numbers to then how we would solve an equation with matrices, because the processes are the same, or rather the idea is the same. It's just obviously one you're working with just numbers and one you have matrices, so that part is different. But I want to look at what's on the left here first, because this is what you would just do with real numbers. So if you had an equation ax equals b, where a and b are just numbers, so as an example, 3x equals 5 would be a more concrete example for you. If you were to solve for x, because ultimately when you solve an equation, you're solving for the variable, what would you do first to solve for x? Divide by 3. So with matrices, though, because we're now transferring this idea over to matrices, we can't divide by matrices. We don't have matrix division. So rather than dividing by 3, what this step is showing here is we are really multiplying, or we could multiply by 1/3 on both sides. So dividing by 3 and then multiplying by 1/3, it's the same operation. But rather than dividing, we refer to that as multiplying by the inverse. For multiplication, the inverse is the reciprocal. So Why we're describing it that way is rather than dividing multiply by the inverse is because yesterday we learned how to find the inverse of a matrix and we know how to multiply matrices. So we can multiply both sides of a matrix equation by an inverse. And that's what it's showing here. So to solve for x in a matrix equation, just like we would for real numbers, we can multiply both sides by the inverse of matrix A, because then we know, or we saw yesterday, when you multiply an inverse and its matrix, that product is the identity matrix I. And it shows over with the real numbers as well. When we multiply 1/3 and 3, multiplicative inverse is always multiplied to be 1. And when you have 1 times x, that's just x, that gives you your solution. Same thing with matrices. The identity matrix is the equivalent of the number 1. So when you multiply the identity times matrix x, it's just equal to x. And then this gives you the solution to that equation. So this is always going to be the form that your solution is in. So it's not just in one case, this is how you do it. In all cases, this is how you do it. So if you set up a matrix equation that's in the form A times x equals b, your solution, x, is always going to equal the inverse of matrix A, so the inverse of your coefficient matrix, multiplied by your constant matrix B. And you would find that product, and that gives you your solution. So this is what you would need to know to solve a matrix equation. It's always going to be in that form. You do not ever have to show all of these steps. You just have to show this to find your x. So we're going to go through an example so you can see this. What this says here is just what I just pointed out, that we have the inverse of the coefficient matrix times b to find your solution always. So in example 1, it says use a matrix equation to solve the system of equations. So you will have at least one problem on your test that will have you solve a system this way. So you do need to know how to use a matrix equation to solve a system. And here's my system here. So I'm going to set up, just so all of you know how to set up a matrix equation when you are given a system. And it's always going to be in the form A times x equals b. And your matrix A is your coefficient matrix. So the first column should be the column of x coefficients, and that's 1 and 3. And then the second column is the column of y coefficients, 2 and -6, times the matrix x is your variable matrix. So since our two matrices are x and y, I'm going to have x over y. Now, just to point this out, because in most equations, it's always the x term followed by the y term, in which case the x would be on top, the y would be on the bottom. Say in both of these equations, the x and the y terms were flipped, so the y terms were actually first. Then I should have y on top and then followed by x. So in order to know which one goes, one over the other, it's which one comes first in your equations followed by which one comes second. Or rather think of it this way: if your x column is first, x should be on top. If your y column is second, y should be on the bottom. And then for your constant matrix B, the constants in these equations are 9 and 3. So that's how you go from a system to a matrix equation. But now to solve it, again, this is the solution every single time. The x equals A inverse times B. And what's written above it, that's the y. This is the solution. So to find my matrix x, I am going to have to find the matrix A inverse. So right now I have my matrix x, which is going to be xy, should equal. I need to know what A inverse is, so that I can multiply it by matrix B to get my solution. So this is what I need to find. And that's what we covered yesterday, is finding the inverse of a 2 by 2 matrix. So off to the side here, I'm going to show the work for finding a inverse, and this is where, if you have your sheet, I mean, I'll show it for this example, but as you're working through problems, you may want this out. So I have the formula that you'll be given for how to find the inverse of a 2 by 2 matrix, and we have our matrix A right here, the 1, 2, 3, negative 6. So I first need to find the determinant of A, because that's going to be this denominator here. So the determinant of matrix A will be, and that's where I start with the product of my main diagonal. 1 times negative 6 is negative 6. And then make sure you are subtracting, not adding, your next product, which in this case is 2 times 3, which is 6. So I have negative 6 minus 6, and that's negative 12. So now to set up A inverse, I have, according to the formula, 1 over, this is the determinant, so 1 over negative 12, multiplied by, and this is where just last hour some students were making mistakes in their solutions because they weren't rearranging the beginning matrix to follow the formula for the inverse. So remember, this is rearranged from the matrix you started with. The main diagonal of your starting matrix gets switched. So in this case for matrix A, the 1 and the negative 6 change places. And then the other diagonal, the B and the C, those become the opposite. So because 2 and 3 here are both positive, now they're both going to be negative for the inverse. And then I need to then multiply every element in that matrix by 1 over negative 12, or rather divide them all by negative 12. So if I have negative 6 divided by negative 12, that'll be positive, and 6 over 12 is 1/2, so it's positive 1/2. If you wrote 0.5, that's okay. And then negative 2 over negative 12 is positive, 2 over 12 is 1/6. And then negative 3 over negative 12 is positive, 3 over 12 is 1/4. And then 1 over negative 12 will just be negative 1/12. And really, in this matrix, if you didn't have the fraction simplified, that's okay. If I just wanted the inverse as your answer, you should simplify it. But if you don't simplify it to then use it in the problem, ultimately the final answer is what should be simplified. So this matrix is A inverse. So that's the matrix that goes here and gets multiplied by matrix B. So I'm just going to fill in what we got for our inverse matrix. And then we can go ahead and multiply. When multiplying these two matrices, I just want to point this out as well. This matrix here, A inverse, is a 2 by 2 matrix. And this matrix B has 2 rows, 1 column. It's 2 by 1. So what are the dimensions going to be of the ending matrix? 2 by 1. So the 2's are the same here. That means we can multiply them. The 2 and the 1, those are the dimensions of your answer. So you should get 2 rows, but just 1 column. And that might help you think about how to multiply these. I multiply the rows in the first one by there's only 1 column. So each row gets multiplied by that 1 column. So I would have, if I multiply the first row by that column, I multiply the 1/2 and the 9, and that would be 9/2, or if you wrote 4.5, it's okay. And then plus 1/6 times the 3, that's 3 over 6, that's 1/2. Okay, so that's going to get added together, that's one number. Now I do the same with row 2 by that column, 1/4 times 9, that's 9/4, plus 2. And then plus negative 1/12 times 3, that's negative 3/12, which is negative 1/4. So now I'm kind of running out of space here. But now if I simplify these, ultimately, look, it's supposed to equal your xy, meaning your top number is your x value, your bottom number is your y value. So on the top, I'm adding 9 over 2 plus 1 over 2. That's 10 over 2. That's 5. And then on the bottom, 9 over 4 plus negative 1 over 4. That's 8 over 4, and that's 2. So this shows my x value is 5. Bless you. My y value is 2. Bless you. So the solution is the ordered pair 5, 2. Okay, so I'm going to recap the steps just so you understand. Really, there's two main steps to this. I know there's a lot of little steps in between, but there's two main steps. Once you have your matrix equation, your first step is to find A inverse. That's really ultimately what you need to do first. You need the inverse of matrix A. Your second step then is to multiply A inverse by matrix B, and that gets you your solution. So find the inverse of A, and then multiply it by matrix B, and you have your solution xy. Okay, so I would like you, I'm going to leave this up on the screen in case you're still writing things down, or I know example 2's on the back, so if you don't want to keep flipping back to what you wrote down, you can look up here as well. But I would like you to work on example 2 on the back. So solve the system of equations in example 2. I know band and choir people, you're going to have to leave, and there is a worksheet for your assignment. So this is the only example I'm going through with all of you. Example 2's on your own, and then the rest of the time is work time. So if you do have to leave, I'll come around and get you all the assignment as well, because I know you're going to have to get going.